Hello everyone, welcome to Serious Questions and Answers based on the Computational Finance course. Today is question number 29 out of 30, therefore we are almost finishing the first volume of this series. The question of today is how to calibrate a pricing model, how to choose the objective function. In general, if we consider calibration problem in finance, calibration is sort of an art. There is no one given recipe that always works for all the pricing methods and also all sorts of models. Every approach, every calibration, it is an art because you have to understand your model very well and you have to be very skilled to get your good calibration in place. However, there are a number of principles and things that you should look at if we want to calibrate your model. If we have a stochastic volatility model, for example, like a Heston or Bites or other models, and those models will normally be used to price some exotic derivative, like for example forward start options or some callable derivatives. If we have a derivative, for example, that will expire in 5 years, and so it depends on the volatilities from today until 5 years, then as you can imagine, it will be very pointless for such a model to be calibrated to instruments that are 30 years away from now or 40 years and so on. Therefore, it's an art because you should only consider instruments that are relevant for your derivative. How to see whether something is relevant for your model or not? This can be seen from the perspective of sensitivities. If you would change your volatilities, so if you have market instruments for volatility surface and you change all of them one by one and you revalue your derivative, and if your value of your derivative changes, this means your derivative is sensitive to that particular market quote, market instrument. So in principle, you should always calibrate your model to the instruments that your model is sensitive to. In the case of the volatilities of pricing of some exotics, those will be European type of options. And here it's also important not to calibrate to something which is irrelevant, because you don't want to lose you don't want to use all the flexibilities for the, let's say, long-term options while your derivative pays in a short end. So then you have to reconsider type of or rethink of instruments that you really want to use for calibration. And from the trading's perspective, for traders' perspective, it's important that your calibration takes place to instruments that exist, that can be bought or sold in the market, because that's relevant for a trader. So let's take a look further. So those are 2 points I just mentioned, that normally if we have an exotic derivative, we would calibrate it to European type of options. And the reason for that is that those are typically the most liquid instruments available in the market. If you have an exotic derivative, and there are more exotic derivatives, however, a little bit simpler, available and liquid in the market, then very likely those will be your instruments that you like to offset your hedge, you set up your hedge. In general, however, that's difficult. If we are in exotic world of exotic derivatives, then a standard approach will be go into the European type of options. And then, so that's the first thing. Second thing, only calibrate to relevant market instruments. Don't calibrate to everything and say this is the best. No, you should only use the instruments that are relevant for the hedging purposes. There are a few ways how you can define your objective function. So for example, here, this is the standard weighted target function. By the way, in the book, I'm defining, and actually there is much more details on type of calibrations you could have, and more information also you can find in lecture number 13. So if you are interested in that, please revisit. So let's go back here. So if we have a standard error, so this is your calibration, the target function in your optimization that you would run to find the optimal parameters for your stochastic volatility model, for example, of some model that you have. So you choose a model, this model has parameters. Your objective is find these parameters such that the model generates the same prices, option prices, as the ones you see in the market. This means that we will define a summation over all the expiries, all the option expiries, all the relevant strikes with some weights omega. And then what we will do here, we will look at the difference between option price available in the market. So this is market, and this is model here. And theta represents a vector of model parameters. So we could have a theta1, theta2, and so on. So this is a vector that we would like to optimize. We would like to find optimal parameters, theta1, and so on, such that the difference, the square difference between market and the model is as small as possible. If this error or this difference is 0, this essentially means that you have perfectly calibrated your model to the market data, and that's always very good. Then we also have this weighting function here. So this is something important. This weight here could be a tuning parameter for you. For example, imagine a scenario that you have a calibration of your model. So if we have a market implied volatility, so we have here, this is an axis for strike K. Here we have implied volatility. Here's at the money level, so ATM. We have market data is like that, so there's some smile, and your model calibrated almost just like that. There is some difference here. Maybe let me revert. Let me do something like this, like that. So this is your model. Let's call it. This is market. This is model. Okay. So we see that actually in this case, if you would take your Black-Scholes model and you would calibrate only to at the money, then at the money options will be better from the Black-Scholes model than your, let's say, advanced stochastic volatility framework. And this is not good. Always, if we consider model and we would like to calibrate this model, the objective is to first make sure that you are able to calibrate at the money options. This part, therefore, is always the critical part. If you have any smile, any skew, always make sure whatever happens outside, this is the point, at the money point where the market and your model has to match, and the rest is extra. If you have nice fit to the smile. So for example, let me give you an example here. Suppose this is the market and your model is like this. Then you could say, look, it has a very similar smile to one in the market. But if this is at the money here, this difference is huge, because if I would just calibrate Black-Scholes to this point, it will be performing much better, depending of course on derivative, than your exotic model that allows you to generate smile or skew. So at the money point is the critical point. It's always the most important. And this is what you can actually do here. You can calibrate, so you can put extra weights to make sure that in your optimizer, you will have extra weights for at the money. So for example, you could here put, if you have at the money options, this becomes 10. So put extra weight for the middle at the money options. There is a second approach, which says that we could also not look at the option prices, because here you had, I call it C, but this could be call or put option prices. We could also take a look at the implied volatilities. So we take this option price, we use Black-Scholes inverse formula, let's say a technique to find implied volatility, and the same we will do here. So instead of looking at option prices, we can just calibrate the model based on implied volatility formulas. This has advantages and disadvantages. Advantage is that small differences in option prices may lead to huge differences in implied volatilities. Therefore, if our objective is always to have implied volatilities perfectly matched, which naturally would imply option prices to be matched. But it can happen that small differences in prices give you significant differences in implied volatilities. So this is always preferred. However, there is a price to pay, because if we calculate implied volatilities for calls, so this part is kind of easy and cheap, because if we have market quotes for expiries and strikes, you can pre-calculate implied volatilities for all of them. Then you keep it, it doesn't change. However, the ones that come from model, for every change of your model parameters, theta1 and so on, you have to recalculate your implied volatility formula. This means that it can be much more expensive than this case, because here we know we can do it with Fourier transform, for example, but if we want to have implied volatility formula and we don't have it, likely you don't have it in a closed form, then you always have to do Newton-Raphson or Brent's method to calculate implied volatility. So this is basically our preferred choice. However, computationally, this is much more expensive. There is also another approach where actually it's very much related to the omega ij here, where we would calibrate only to out-of-the-money calls and out-of-the-money puts, because these are typically the most liquid instruments in the market. So if you look at the market quotes that you can see yourself, the most information is out-of-the-money options. Why is that? Because if the option becomes deep in the money, then the majority of the information is in intrinsic value. Intrinsic value means that if I have a maximum, let's say maximum ST minus K, if I look at the ST0, for example, minus K, this is the intrinsic value. So if it's deep in the money option, then there is a very little information which comes from the volatility, because then option converges to the intrinsic value. So if I look here, then as a function of ST, then we actually see that at some point, this option grows in time, because this value, at some point, if ST goes up, it becomes larger than K, so this is our K, becomes just linear and grows linear ST. And the important part is actually happens here, before we get to this strike level. So this is a relevant part, which gives us information about the volatilities. Later is less important, because if we have deep in the money options, the intrinsic value is the leading term. This is what you don't want to have in your calibration. You want to be sensitive to the market information, not to the intrinsic value that is just there in the option values. But this, however, you can do it, you can vary omega ij's such that your formula becomes only out of the money options for calls and puts, with extra weights for at the money level. So this is basically the main principles and main issues that you may encounter when dealing with model calibration. There is no single recipe that you can apply to calibrate any model to any derivative. Typically, you have to just investigate on a case-by-case basis to find out what is the best approach to calibrate your model. And if you calibrate your model, always double check with your pricing back market instruments. So this is very, very important. Are you sure that your at-the-money implied volatilities from your model match the ones from the market? It's really, really critical. I hope it explains, I hope it gives you a little bit of flavor how to approach the problem of calibration. And see you next time. Bye-bye.